Welcome to the Deep Dive. Today we're plunging into a world that's, well, it's all around us, often invisible, yet it fundamentally shapes our daily lives. Have you ever considered something as simple as, say, your morning coffee cup? Or maybe something as life-saving as a bicycle helmet?
Mm.
What about a cutting-edge artificial heart valve? Believe it or not, these incredibly diverse items share one powerful, invisible commonality: synthetic polymers. So today we're taking a deep dive into the fascinating universe of these materials, how they're built from the ground up, how we classify their amazing variety, and what truly makes them behave the way they do. We've pulled together a stack of expert sources to give you the ultimate shortcut, really, to becoming well-informed on this ubiquitous topic.
It's true. What's truly remarkable is just how foundational polymers are to our modern existence. I mean, we're talking about a multi-billion-dollar industry.
Yeah.
Site manufactures trillions of pounds of these materials annually. It impacts everything from the clothes on your back to advanced medical devices. Our mission today is really to cut through the dense chemistry, give you a clear, practical understanding of these materials, highlighting the aha moments you might miss otherwise.
Yeah, absolutely. And as we journey through this deep dive, we'll keep coming back to real-world examples, including that intriguing mention in our sources about bullet-resistant glass, which, by the way, isn't truly bulletproof, apparently,
Right, that's a key distinction.
and why polymers are absolutely key to its incredible protective power. We'll unpack that. So let's start with the absolute basics. What exactly is a polymer?
Okay.
Think of it like building with Legos, maybe. Each individual Lego brick represents a small molecule called a monomer.
Right, the building block.
Exactly. And when you connect hundreds, thousands, or even millions of these identical or similar bricks together to form a giant complex structure, well, that entire structure is your polymer. It's just a huge molecule made of these repeating units.
And if we connect this to the bigger picture, it's important to remember there are basically two main categories of these molecular giants. First, you have biopolymers. These are the natural ones produced by living organisms.
Like DNA.
Exactly. DNA, RNA, proteins, polysaccharides like cellulose in plants or chitin in insect shells. Complex stuff.
Right.
But our focus today is entirely on synthetic polymers, the ones meticulously crafted by scientists and engineers in labs and factories.
Ah,
These are the building blocks for your plastic bottles, durable carpet fibers, or those artificial heart valves we mentioned earlier.
and the naming often reflects this, right? This building block idea.
Yeah, quite often, chemists frequently name the polymer directly from the monomer it was derived from.
Yeah.
So if you take the monomer propylene and polymerize it, you get, well, you guessed it, polypropylene.
Simple enough.
Sometimes, if the monomer name has two words, like vinyl chloride, you'll see parentheses in the polymer name, like polyvinyl chloride. And you might also know them by their popular trade names. Like Teflon, that's actually polytetrafluoro.
Teflon, right. Okay. Now here's where it gets, I think, really interesting. What if you don't just use one type of Lego brick? What if you mix and match different kinds of monomers?
Ah, yes, copolymers.
That's when you create something called a copolymer. It's not just one type of repeating unit, but two or more. It creates a much more complex and often more versatile material.
That's right. And the crucial question then becomes, how do those different monomers arrange themselves along the chain? We see a few distinct patterns. There are alternating copolymers where the units just alternate, AB, simple.
Got it.
Then you have random copolymers where, well, the name says it all. The distribution is completely haphazard.
Okay.
Next, block copolymers are pretty cool. They feature long segments or blocks of one homopolymer connected to long blocks of another, like a long string of A's followed by a long string of B's.
Right, like sections.
Exactly. And finally, graft copolymers. These are a bit like a tree. You have a main chain of one type with sections of another type grafted onto it, like branches.
Interesting visual.
And the beauty of copolymers is that they often exhibit entirely new and frequently superior properties compared to their individual parts. Think of saran wrap for food packaging.
Oh, yeah.
Or that incredibly tough ABS plastic used in crash helmets and luggage. Those are all clever copolymers engineered for specific jobs.
Fascinating. Okay, so we've talked about what polymers are, how the building blocks arrange. Now let's dive into how these amazing materials are actually formed, the chemistry behind it.
The reactions.
There are two primary categories based on the reaction type: addition polymers and condensation polymers. Let's start with addition polymers. These are formed when monomers simply add to one another, like continuously adding Lego bricks to a growing chain.
Right.
Crucially, no atoms are lost in this process. All the atoms from the original monomers end up in the final polymer chain. This usually happens by breaking double bonds in the monomers and forming new single links.
Exactly. And the specific ways this addition can happen involve different chemical mechanisms like radical, cationic, or anionic addition.
Okay, let's break those down. What's radical polymerization?
So radical polymerization is a very common method
Yeah.
used for many everyday plastics. It's kicked off by a radical that's a molecule with a highly reactive, unpaired electron.
Unstable.
Very. This radical attacks a monomer, starting a chain reaction. The chain grows by adding one monomer at a time, propagating, until two radicals bump into each other and terminate the growth. It's how simple ethylene gas becomes that versatile polyethylene we use everywhere. Plastic bags, milk jugs.
Gotcha. So what about cationic?
Cationic polymerization, in contrast, works best for monomers that have groups that kind of donate or push electrons towards the reactive site. Imagine a positive charge moving along the growing chain, attracting new monomers. An acid catalyst starts it, creating a positively charged carbon atom, a carbonation on the monomer. This reactive carbonation then attacks another monomer, propagating the chain. Those electron-donating groups are really important because they help stabilize the positive charge, letting the reaction proceed smoothly. Isobutylene, for instance, polymerizes really well this way.
Makes sense. And the third one, anionic.
Right, anionic polymerization. This method is efficient for monomers that have groups that withdraw or pull electrons away from their reactive site. The opposite, really.
Okay.
Here, a highly reactive, negatively charged ion, an anion, starts the process. It attacks the monomer, creating a new negatively charged carbanion. These electron withdrawing groups are vital because they stabilize that negative charge. But what's really fascinating about anionic polymerization is that under the right conditions, the chain doesn't truly stop growing until you deliberately add something to terminate it, like water.
So it just keeps going.
Yeah. If you keep feeding it monomers, the chain just gets longer and longer. That's why they're often called living polymers.
Living polymers, wow.
They stay active, ready to grow. It allows for incredible control over the final length and structure, which is crucial for, high-performance materials.
So, okay, real-world example time. What does this mean for, everyday stuff?
Think about superglue. That incredibly strong adhesive. It's methyl cyanoacrylate. It has two powerful electron withdrawing groups.
Right.
That makes it so reactive that even a weak attacker, like the tiny bit of moisture on your skin, is enough to kick off its anionic polymerization. That's why it bonds so tightly and quickly to your skin. Your own moisture acts as the catalyst.
That explains a lot.
Yeah, and doctors actually use compounds very similar to superglue, like Dermabond, to close wounds sometimes. It's a quick, stitch-free option. A neat example of that controlled, living polymerization in action.
Amazing. Okay, so that's addition polymers. Let's shift gears to the second big category. Condensation polymers. How are they different?
Well, unlike addition polymers, these are formed when monomers join together. But, and this is the key, a small molecule, like water, or maybe CO2 or nitrogen gas, is lost or condensed out in the process.
Something actually leaves.
Exactly.
Yeah.
Imagine those Lego bricks clicking together, but maybe a tiny bit of plastic breaks off each time a link forms. It's often like a dehydration reaction removing water to make the bond.
Okay, examples.
Polyesters are classic ones. Take polyethylene terephthalate, PET, that's your soft drink bottles.
Right.
It's made by a series of reactions where water molecules are kicked out with each new bond. Nylon 646, hugely important for fabrics, engineering plastics, that's another condensation polymer, made from two different monomers releasing water. And if we connect this back, polycarbonates, like Lexan, are also condensation polymers.
Lexan. That sounds familiar.
It should. Structurally similar to polyesters, but with repeating carbonate groups. Lexan is remarkable stuff, lightweight, transparent, but with incredible impact strength.
So used for
all sorts. Bicycle helmets, CDs, DVDs, and yes, it's a key component in that bullet-resistant glass we mentioned way back at the start.
Oh, there it is.
Its ability to absorb and distribute impact energy is exactly why it's chosen for critical safety applications. It's a condensation polymer doing some heavy lifting.
Okay, so we've got the reaction types, addition and condensation, but you also mentioned classifying them by how they grow, chain growth versus step growth.
Yeah, that's another way to look at it. It's about the mechanism of assembly. Chain growth polymers, which often includes our addition polymers, grow by adding one monomer at a time to a single, highly reactive spot at the end of the growing chain.
Like that train adding one car at the front.
Exactly that analogy. The monomers themselves don't react with each other, only with that active end. Step growth polymers, on the other hand, are different. They form when individual monomers react with each other to create small chains, first oligomers.
Oligomers.
Just a few monomers linked up. Then, these oligomers react with other oligomers and even more monomers to build bigger and bigger polymers. This usually involves monomers that have at least two reactive points, meaning everything monomers, oligomers, can potentially react with everything else. It's more like building a network piece by piece.
So is there a direct link? Like addition polymers are always chain growth and condensation are always step growth.
Generally, yeah, that's a good rule of thumb.
Yeah.
Most step growth polymers are condensation polymers, and most chain growth polymers are addition polymers. But there's always an exception, right?
Of course.
Polyurethanes. They're technically addition polymers. No small molecule gets lost.
Okay.
But they're considered step growth polymers because their chains grow from multiple reactive points, not just that single active site at the end. It's a subtle but important difference in how they actually assemble.
Huh. Okay, that's interesting. So different reactions, different growth mechanisms. But what about their actual shape, their structure? That must affect how they behave.
Oh, absolutely. Profoundly. We can classify them by structure, too.
First, I guess, is branched versus linear, like our Lego chains again. A linear polymer is just a straight string, right?
Yeah.
Minimal side connections,
Pretty much.
whereas a branched polymer has lots of side chains, like branches off that main string. Makes it more tangled, less compact.
Exactly. And this raises an important question.
Yeah.
How do we actually control the branching? Because it matters.
Right.
Well, the development of Ziegler-Natta catalysts was a huge breakthrough. These catalysts let chemists create incredibly linear polymers with very little branching.
How do they do that?
They avoid involving free radicals, which tend to cause uncontrolled side reactions and branching. This control is critical because linear chains can pack together much more efficiently.
Okay, so packing matters.
Big time. Think about polyethylene. Low-density polyethylene, LDPE, used in plastic bags, films, it's highly branched. Lower density, softer, more flexible, but use a Ziegler-Natta catalyst, and you get high-density polyethylene, HDPE. It's linear chains packed tightly. Result: a much stronger, more rigid material for things like milk jugs, squeeze bottles, Tupperware. Same basic monomer, totally different properties, just based on branching and packing.
Wow. And these catalysts do more than just control branching.
They do. They also give us incredible stereochemical control.
Stereochemical.
Yeah.
What does that mean in this context?
So imagine each monomer unit has a little side group attached. If that attachment point is a chiral center, the side group can stick out in one of two mirror image ways, like your left and right hand.
Okay.
Tacticity refers to how these side groups are arranged along the polymer chain. Are they all on the same side? That's isotactic. Do they alternate sides regularly? Syndiotactic. Or are they just arranged randomly? Atactic.
And that arrangement matters.
Oh, hugely. Isotactic, syndiotactic, and atactic versions of the same polymer can have vastly different properties. Stiffness, melting point, clarity. And the cool thing is, with the right Ziegler-Natta catalyst, chemists can often choose which tacticity they want to make. It's like fine-tuning the material at a microscopic level.
Incredible precision.
Okay?
Okay, what about connecting between chains? Not just branches, but linking chains together.
Ah, yes, cross-linking, forming a network.
Right.
The classic example is vulcanizing rubber. Natural rubber is kind of sticky and soft.
Yeah.
But vulcanization introduces sulfur atoms that form disulfide bridges, cross-links between the individual rubber chains.
And that makes it
Much tougher. More durable, elastic, less affected by temperature. By controlling the amount of cross-linking, you can tune the properties. More cross-links generally mean harder, more rigid materials. Fewer cross-links allow for more flexibility and stretch.
okay. And this structure also relates to crystallinity. You hear about crystalline polymers.
Exactly. These microscopic arrangements influence whether a polymer can form ordered structures. Many polymers have regions called crystallites.
Crystallites.
Yeah, these are areas where the chains are lined up, stretched out, and packed closely together in an orderly fashion, held by weak intermolecular forces. These crystalline regions make a polymer hard and durable. The other parts, where the chains are all tangled and disordered, are called amorphous regions. These make the polymer more flexible, often more transparent.
So polymers can have both.
Most do. A mix of crystalline and amorphous regions. The balance determines the overall properties.
Can you give an example?
Sure, back to polyethylene. Linear HDPE packs well, so it has a high degree of crystallinity. It makes it strong and opaque. Polyisobutylene, though, has bulky side groups that get in the way of packing, so it has very low crystallinity, making it soft and rubbery.
And temperature affects this. You mentioned TMNT.
Right. Highly crystalline polymers like HDPE melt at a specific melt transition temperature, TIA. Below TM, the crystallites are stable. Above T, they melt into an amorphous state. Amorphous polymers, or the amorphous regions in semi-crystalline ones, don't melt sharply. Instead, they soften over a range, becoming rubbery at the glass transition temperature, T. Below T, they're hard and glassy. Above T, they're soft and flexible.
Understand TMT must be crucial for using these materials then.
Absolutely. It dictates processing temperatures, service temperatures, whether something will be rigid or flexible in its final application.
Okay, wow. So we've covered how they're built, how they're structured. Let's bring it all together. How do these structural differences translate into the actual properties we see and use every day?
Right, let's classify them by what they do.
First up, thermoplastics. What defines them?
These are polymers that are typically hard and rigid at room temp, but they soften when you heat them. They have a high enough T to be solid, but they can be melted and reshaped, often multiple times.
Like PE bottles, right?
Yeah.
Or PVC pipes and toys.
Exactly. They soften on heating, solidify on cooling, very moldable.
But you mentioned PVC can be brittle.
Pure PVC can be, yeah. So
yeah.
to make it flexible, think vinyl upholstery, raincoats, IV drip bags. They add plasticizers.
Plasticizers. What are they?
Small molecules, often things like dialkyl phthalates. They get in between the polymer chains and act like lubricants, letting the chains slide past each other more easily, makes the material flexible.
But they can evaporate.
Some can, yeah, slowly over time. That's why old vinyl sometimes gets brittle and cracks the plasticizer has escaped.
Ah, okay. Next category. Elastomers.
Elastomers, these are the stretchy ones. Polymers that can be deformed, stretched, but then snap back to their original shape.
Like rubber bands?
Natural rubber is the classic example, yes.
Yeah.
But also synthetic ones like spandex. That's a polyurethane with just a little bit of cross-linking. Gives it that amazing stretch and recovery for swimsuits, athletic wear.
And you mentioned chewing gum.
Get this, yeah. Chewing gum is actually a complex blend, but many of the polymers in the gum base are elastomers. That's what gives it its chewiness. You're basically chewing on synthetic rubber.
Huh. Never thought of it that way. Okay, what about fibers?
Fibers are made when certain polymers are melted or dissolved, then forced through tiny holes, spinnerets, and cooled or dried rapidly.
Like making spaghetti.
Kind of. The process forces the polymer chains to align along the direction of the fiber. This creates oriented crystalline regions along the fiber's axis.
And that alignment gives them
Significant tensile strength. They're strong when you pull on them. Think nylon, Dacron, a polyester, even specially processed polyethylene, used for ropes, textiles, carpets.
Makes sense. And the last property category, thermosetting resins.
Thermosets. These are different. They're highly cross-linked polymers. Once they're formed and cured, usually with heat, they set permanently into a rigid structure.
So you can't melt them again.
Nope, they're set. They are generally very hard, insoluble, and can withstand very high temperatures without softening. Bakelite, one of the very first synthetic polymers from 1907, is a classic thermoset.
Used for?
High-temp applications, old radio casings, electrical insulators, pot handles, even things like missile nose cones, where heat resistance is critical.
Okay, so this wide range of properties.
Yeah.
It brings us back to bullet-resistant glass. How do these principles apply there?
Right. It's a composite material leveraging different properties. You often have multiple layers of regular glass.
Which is hard but brittle.
Exactly. Sandwiched with transparent polymer sheets. Often polycarbonate like Lexan or sometimes polyvinyl butyryl, PVB.
And the polymers roll.
The polymer interlayer is tough and flexible. When a bullet hits, the glass layers might crack, but the polymer holds the pieces together, preventing dangerous shards from flying. More importantly, the polymer absorbs and distributes the impact energy through deformation.
So it's the combination.
Precisely. The hard glass initiates fracture. The tough polymer contains it and absorbs the energy. Multiple layers enhance this effect. That's how it resists penetration, even if it's not truly bulletproof.
Fascinating engineering. Now, polymers are amazing, clearly indispensable. But there's the environmental downside, isn't there? Most traditional ones aren't biodegradable.
That's the huge challenge, absolutely. They persist, they hang around in landfills and oceans for hundreds, maybe thousands of years. Accumulating, it's a massive global problem.
So what about recycling? Can that help?
It can, yes. To mitigate this, many polymers can be recycled. PT, your soda bottles, is relatively easy.
How so?
You can chemically break it back down into its original monomers using hydrolysis, basically reversing the condensation reaction. Then you purify those monomers and make new PT. It's pretty efficient, relatively speaking.
But not all polymers are like that.
Unfortunately, no. Addition polymers like polyethylene or polystyrene are much harder to break back down into monomers chemically.
So what do they do with those?
Usually they get melted down and remolded into new shapes, but the quality often degrades each time, so it's sometimes called downcycling. Or they can be broken into smaller hydrocarbon fragments through processes similar to cracking petroleum, which can then be used as fuel or chemical feedstock.
And those recycling codes, 1 through 7, on plastics?
Yeah, those indicate the type of polymer, globally recognized system. Code 1, PCT, and Code 2, HDPE, are generally the most easily recycled.
But sorting is a problem.
It's a major logistical hurdle. You can't just melt down a mix of different plastics. They don't blend well, and the resulting material is often useless. That's why sorting, often still done by hand, is so critical and costly for effective recycling.
So looking ahead, the big goal must be biodegradable polymers.
Exactly. That leads us to a really important question for the future. Can we design and manufacture polymers that are inherently biodegradable, that can be broken down naturally by microbes in the environment?
Does that happen?
Oh, yes. There's a lot of research focused on this. Creating polymers, often polyesters or polyamides, that have specific chemical bonds like ester or amide linkages built in.
Acting as weak links?
Precisely. Weak links that enzymes produced by soil microorganisms can readily attack and break down through hydrolysis, essentially unzipping the polymer chain naturally. The decades ahead will likely see huge advances here, new biodegradable polymers that can match the performance of traditional plastics, but without the environmental persistence. Imagine packaging that just composts away.
That would be a game changer. Well, that brings us towards the end of our deep dive into synthetic polymers. We've really journeyed from the basic building blocks, the monomers, through how they're chemically assembled, addition, condensation, how their structures vary, linear, branched, cross-linked.
Tacticity, crystallinity.
Right. And finally, how all that translates into the incredible properties shaping our world, from bullet-resistant glass providing safety to superglue holding things together, and even looking towards a future of sustainable materials.
It is pretty amazing. And what's truly remarkable, I think, is considering how chemists, just by understanding these fundamental molecular interactions and reaction types, can design materials with such incredibly specific targeted properties.
Yeah.
And that really raises a provocative thought, doesn't it? As our understanding gets even deeper, as our technology advances, how else might we engineer materials? What currently unimaginable global challenges could we solve by designing polymers we haven't even conceived of yet? The potential seems, well, almost limitless.
A really exciting thought to end on. Thank you so much for joining us on this deep dive. We hope you feel a little more well-informed and maybe a lot more curious about the hidden chemistry that's truly everywhere in your life. Until next time, keep that curiosity flowing.